Good morning. I welcome you all to this session of fluid mechanics. So last class we were discussing the superimposition of the basic flows for an ideal fluid. First we discussed the superimposition of a rectilinear flow parallel to the x-axis with a doublet which generates the streamlines which could have been generated if an parallel ideal flow parallel to this x-axis, a rectilinear ideal flow parallel to the x-axis is deflected by a circular cylinder placed at the origin, whose axis is at the origin. Then next we discussed the superimposition of a rectilinear flow parallel to x-axis plus the doublet at the origin plus an irrotational vortex motion which creates the streamlines that could have been obtained if there is a circulation, a circulation is added in the flow past a circular cylinder, and in that case we showed that the stream function is superimposition of the rectilinear flow and doublet, that is flow past a circular cylinder plus the circulation, that means the stream function for a free vortex. And here we have seen as a consequence, if we find out this term creates the asymmetricity in the velocity field, that if we find out the velocity v theta vr, then we will see that this v theta and vr is like this, that at the surface v theta is this minus 2u sin theta plus gamma by 2 pi a. So therefore we see this is the term which creates the asymmetricity. That means if we see this expression, we will see the tangential velocity at the surface, because surface there is only tangential velocity, there is no radial velocity which is 0 at the surface, which is not symmetrical about this axis, because the sign of sin theta changes. It is positive from 0 to 180 and it is negative from 180 to 360. So therefore this v theta is symmetric about the y-axis but not symmetric about the x-axis. That means the velocity field in this half is different from that in this half. And another very interesting thing we found, that the stagnation point is not occurring like a flow past a cylinder, that means superimposition of only the rectilinear flow and the doublet, that means this is the equation for that, like where the stagnation points occurred at theta is equal to 0 and theta is equal to 180 degree. So unlike that, here the stagnation point occurs at different positions depending upon the cases that the sign of this quantity. That means for stagnation point we can write v is equal to 0 and we arrive at the equation sin theta is gamma by 4 pi a. So depending upon the sign of this quantity, the existence of the stagnation points the existence of the stagnation points depend on the sign of this quantity. There are three possible situations. One is gamma by 4 pi au less than 1, another is gamma by 4 pi au is equal to 1, another is gamma by 4 pi u is greater than 1. And depending upon those cases, we have discussed earlier that if gamma by 4 pi au is less than 1, then the stagnation point occurs on the cylinder but it is shifted upwards like this. Then the streamline patterns are like this. If it is exactly equal to 1, so the stagnation point takes place at theta is equal to pi by 2 instead of theta is equal to 0 or 180 degree. Unlike the parallel flow in a cylinder, it occurs at theta is equal to pi by 2. So gamma by 4 pi u greater than 1, it is impossible to define the sin theta by this equation. Well, it means that there is no stagnation point on the surface of the cylinder. So stagnation point is shifted here in the flow field. Now we will find out the pressure expression. Let us see what is the pressure distribution. Now if I write the pressure distribution, write the Bernoulli's equation at far upstream point, that means at some point far upstream where the undisturbed pressure is P infinity and the rectilinear flow velocity is u square, as we did in case of parallel flow past a cylinder, that means superimposition of rectilinear flow and the doublet. Here also we are doing the same thing. Then we write P plus half. Now what is the velocity at the surface of the cylinder? That means if we take at any point on the surface of the cylinder, this is the velocity at the surface of the cylinder. Vr is 0, only velocity is the tangential velocity. That means minus 2u sin theta plus gamma by 2 pi a whole square. Now if I write this, then we can write P. Now if I make this, clear this expression, then it will be 4, that means 2u square, half rho you can take common, okay, you can take half rho as usual, rather 4 u square sine square theta minus 2u sine theta gamma by pi a plus gamma square by 4 pi square a square, square of this term. Now you see the P infinity is constant, this u is constant, this is defining the rectilinear flow, gamma the circulation strength is constant for the free vortex flow, pi a these are constant. So we can write, taking all constants together, P is some constant, only the sine functions minus half, if I just take it 2, it will be 2 rho u square sine square theta minus rho u gamma by pi a sine theta. So P can be written as some constant. So we are taking this we are taking this side P infinity plus half rho u square minus this quantity as constant minus 2 rho u square sine square theta minus, of course, this is this minus this. So this becomes plus. So this becomes minus. So this becomes plus. Plus what we get? Rho u gamma by pi a sine theta. Now it is very clear that this is the term which is responsible for the asymmetricity. Means what? That let us consider this cylinder here. Now let us consider this is the free stream velocity. So this is the free stream velocity. Now if we want to find out, now this is the pressure distribution. As I have told, the only force on the surface of this cylinder is the pressure force, because the viscous force, that is the force along the tangent at the surface, along the tangential direction at the surface, is 0 because of the fact that fluid is inviscid. So therefore, if we again want to find out the force in x and y direction, then what is Fx and Fy? In the similar fashion we take that if this be the P for an elemental sector or circular arc of the surface which subtends d theta angle at the center, and this angle is theta, we see that we already recognized Fx is P, A is the radius, this is A, this radius is A, P A cos theta d theta from 0 to 2 pi, earlier also we did like that, and Fy with a negative sign, y is directed, positive directed upwards, so P A sin theta d theta. Now here if you see that if you multiply this with cos theta, this term gives 0, this becomes the symmetric term from 0 to 2 pi. That means integral of sin square theta cos theta from 0 to 2 pi, if you perform this integration, it is very simple from the trigonometric function that it will be 0. Similarly, the integration of sin theta cos theta, which gives sin 2 theta from 0 to 2 pi, also will be 0. So which means that in Fx direction there is no force, 0, which physically means that the pressure forces are symmetrical about the y axis. That means the force exerted on this hub is exactly equal to that on this hub in the x direction, so that ultimately this gives 0 force. But what happens in Fy direction, if you see carefully, if you multiply this expression of P with sin theta, then you will see this will give a sin square theta term here, and this will give a sin cube theta. Now sin cube theta d theta 0 to 2 pi, if you make the integration, this will give 0, because this will give an integration of sin square theta sin theta d theta. So this we will get a 0 term. That means the integration of sin cube theta d theta will be 0. Whereas this even term sin square theta d theta will not give a 0 term. So this is because of this term we get Fy a non-zero value, and if you just perform this equation, now we write only this term. So therefore Fy exists only for this term, rho u gamma by pi a with a negative sign into 0 to 2 pi sin square theta d theta, and this becomes equal to, with a negative sign, rho u gamma. Oh, a cancels because a is there, a will not, simply rho u gamma. So therefore we see that the force in the y direction, force per unit length of the cylinder in that per unit length of the cylinder, the net force in the y direction is minus rho u gamma. This minus sign means the force is on the downward direction. So the sign convention comes from the relative direction sign of the rectilinear flow and the irrotational vortex. Here we have considered the rotational vortex positive in anti-clockwise direction. So for a rectilinear flow which is positive in this fashion, parallel to positive x direction, means I can tell that for a rectilinear flow from left to right and for a rotation or a circulation or a vortex motion in an anti-clockwise direction, the pressure forces on this half, upper half of this cylinder is more than the lower half, so that there occurs a net downward force in this transverse direction to the flow direction, whose magnitude per unit length of the cylinder is minus rho u gamma. So therefore we see in this case, if you add a rotation or a circulation by imposing a vortex motion along with the rectilinear flow and the doublet motions, then we get a net force either downwards or upwards in the transverse direction to the direction, that means the perpendicular direction to the direction of the flow. Now if we make a clockwise direction positive, if we make a clockwise direction positive, or if we add a vortex motion in a positive, in a clockwise direction, then the net force will be in the upward direction. So this phenomena is known as Magnus effect. Magnus effect. That means if we add a circulation in a cylinder, flow past a cylinder, parallel flow past a cylinder, then a transverse force is observed. That means the cylinder is deflected transversely, because of this transverse force is observed. That is the force in the perpendicular direction to the direction of flow, which is known as the Magnus effect. And the deduction of this force per unit length is rho u gamma, and it has been shown that this force is equal to rho u gamma. So I am not taking the sign here, it depends upon the relative direction of the rectilinear flow or parallel flow and the circulation or the vortex motion. So the magnitude is rho u gamma per unit length. It can be proved, and it was proved that for any body immersed in an ideal flow experience a transverse force per unit length rho u gamma if a circulation is added along with a parallel flow past this body, and it was first deducted by two scientists, Kutta, German scientist, and Joukowski, and that's why this is known as Kutta-Joukowski relation. This is known as, and this force is known as lift force if it is in the upward direction. So therefore you see that depending upon the direction of the vortex motion, there is the direction of the transverse motion is created, depends. So the net result is that if there is a circulation, now how this circulation is added, now I tell you that this circulation is added if we have seen that if we combine rectilinear flow with the doublet, we get the parallel flow past a cylinder. Let me show this thing, that parallel flow past a cylinder. That means a simply parallel flow past a cylinder, which is the combination of rectilinear flow and the doublet. That means if a parallel flow U, which is approaching from a far stream, undisturbed condition, this is U, if it is deflected by a cylinder which is placed at the axis, then the streamline is like that. This is the static cylinder. It is the combination of rectilinear flow and the doublet. In that case, flow is symmetrical about both this axis x and y. That means if we integrate, there is no force. Both the velocity and pressure field is symmetrical about both OY and OX axis. That means Fx is equal to Fy is equal to both of them vanish identically. That means there is no net force in the x direction, there is no net force in y direction. That means the pressure distribution is throughout symmetric. That means we get a spherico-symmetric pressure distribution. You understand? Okay. But if you superimpose an irrotational vortex, which means physically that if you give a rotation of the cylinder, depending upon the direction of the rotation, if you give a clockwise rotation, then we will see a net upward force is acting on the cylinder in y direction. Now what happens is that if we give a clockwise rotation, then what will happen? The velocity field will be asymmetric with respect to this axis, while it becomes symmetric with respect to y axis. Let us consider a clockwise rotation. If you give a clockwise rotation to this type of rectilinear flow from left to right, what happens? This increases the velocity in the lower half, while this decreases the velocity in the upper half. So this decrease, if you give a clockwise rotation, what happens? The velocity in the lower half is decreased while the velocity in the upper half is increased. So if the velocity in the upper half is increased, that means the fluid is accelerated in the upper half. so the pressure is lowered, so pressure is low on the upper half. Whereas when the fluid is decreased, you see depending upon the direction of the rotation, the fluid velocity is decreased in the lower half, so pressure is high according to Bernoulli's theorem. As a result, there is a net pressure force in the upward direction. So imparting the rotation to the cylinder implies in some half, upper half, the fluid is, for example, in this direction, fluid velocity is accelerated, in other half fluid velocity is decelerated. If we give a rotation in the opposite direction, which we did first, in that case what happened? It decelerated the fluid flow, that means decreases the velocity in the upper half and increases the velocity in the lower half. Depending upon that, the pressure will be decreased in one side and increased in other side, and will create a net transverse force in the direction perpendicular to the direction of flow, which is known as Magnus effect. And if the direction of rotation and the rectilinear flow such that this transverse force in the upward direction, that means in the direction opposite to the weight or the gravitational force on this cylinder, then this force is known as the lift force. And this is the way the lift force is generated. In fact, in practical cases, the rotation is not given, rather the shape of the body is made in such a way that when the fluid flows past it, it automatically creates a circulation and makes a change in the velocity field in the upper and lower half, because of which the pressure field changes and a net force in the transverse direction upward is generated, which is known as the lift force, and which balances these weights or lifts this body in air. And that is precisely, now I can tell you, the principle used in designing the shape of the aircraft wing, which is known as the aerofoil section. The wing of the aircraft or the aerofoil section is generated in such a way that when the flow past this section, the velocity in the upper half is accelerated, that means pressure is accelerated, the pressure is reduced, and the velocity in the lower half is increased where the pressure is velocity is reduced where the pressure is increased. So a net positive upward force is generated, which is known as the lift force. Okay, then all right, this is the end of the chapter on, or the discussion on, flow of ideal fluids. So today actually we will be starting a new section or chapter, that is flow of ideal fluids, or flows of, sorry, not flow of ideal fluids, flows with a free surface, that is the flow of fluids or flows with a free surface. Now so far we have seen that the flow is taking place in a confined passage where the boundaries of the flows are solid, that means flows are bounded from all directions by solid boundaries. But it is not always necessary that in all classes of flow the flow will be bounded by solid boundaries. There are classes of flow where one of the boundaries are the free surface, one of the boundaries is the free surface of the liquid. This happens in case of flow of liquids. There are instances where the flow of liquids takes place with a free surface as one of the boundaries. Other boundaries are the solid boundaries. These are the flows, they are known as flows in open channels. Flows in open channels. One of the examples is the flow in open channels, where the top surface is the free surface. Now in difference between this class of flow and the flows in confined duct, where the flow boundaries are all bounded by the solid surface, is that in a closed duct the flow takes place because of the energy gradient, and mainly it is the piezometric pressure drop which is responsible for a flow. For the flow of a real fluids, you get a piezometric pressure drop. It is the difference in static pressure plus the elevation head which makes the flow responsible. But in case of flow with a free surface, we see that it is the difference in the elevation part, that means the weight of the body, rather than the static pressure, which makes the flow possible. If there is a free surface in the flow, so for example, flow takes place through a channel where there is a free surface is maintained, then from one section at upstream to another section at the downstream, static pressure remains constant. This is because of the fact that the upper surface is exposed to atmosphere, the pressure is atmospheric pressure. So if we find out the differences in piezometric pressure, it is mainly due to the differences in the elevation head, and it is due to the differences in the weight of the element, weight of the fluid element. So flow is responsible by the weight of the fluid element in these cases. These flows are flows with a free surface, and an example of this flow is the flow through an open channel. The practical examples are open channel is there in artificial canals, in irrigation ditches. So you can have this type of examples. So first of all, we will discuss the different terminologies for flows with free surface. Then we will go to the basic flows and their deductions. Let us see the certain terminologies. Now, what are the terminologies in flow through open channels? One is the depth of flow. One is the depth of flow. Depth of flow H. How do you define the depth of flow? First terminology. Now, depth of flow is defined. Let us consider the flow through a channel flow. So, depth of flow is the, like that, this is the channel bed, this is the free surface. So, depth of flow is defined as the vertical distance of the bed of the channel, this is the bed of the channel, from the free surface. This is the free surface of the liquid. So, this is the free surface flowing over a channel. Let channel, if you look from this direction, you get that, let the channel cross section is like that, a prismatic cross section. So, this is the free surface, this is the channel. So, therefore, this is the bed. So, it is the depth at any section. Depth of flow is defined at any section. It is the vertical height of the bed or vertical distance of the bed from the free surface, or the vertical height of the free surface from the bed. This is known as depth of flow. Another terminology is very important. It is known as top breadth. Top breadth. Top breadth is the breadth or width, that is B, at the free surface. That means this is the cross section. If this be the cross section of the channel, so this is the top breadth. That is the breadth or width at the free surface is known as top breadth. Another is water area. The word water is used because the liquid in practice is water always. So, therefore, this is the cross sectional area perpendicular to the direction of flow. That means this area. This may or may not remain constant in the direction of flow depending upon the design, geometrical design of the channel. So, this therefore, water area is the area perpendicular to the direction of flow. Well, another is this weighted perimeter. Weighted perimeter. What is weighted perimeter? It is the solid, is the perimeter of the solid which is in contact with the water or the liquid. So, perimeter of the solid which is in contact with the liquid is the weighted perimeter P. This is A. And hydraulic radius here in this concept, hydraulic radius in this context is defined RH as RH is equal to A by P. RH is defined as A by P. So, we see the terminologies which are defined and we will refer to frequently afterward. One is the depth of flow, that is the vertical distance of the bed of the channel from the free surface. Another is top breadth, that is the breadth at the free surface in the channel. Water area is the cross-sectional area perpendicular to the direction of flow. So, this is the water area. So, this is the cross-sectional area of perpendicular to the direction of flow. Weighted perimeter is the perimeter of the solid which is in contact with the water or the liquid. And hydraulic radius RH is A by P, that means the ratio of the water area to the weighted perimeter. So, these are the terminologies defined in free surface flow, flows with free surface. Now, we will discuss different types of free surface flow or different types of open channel flow, rather you write open channel flows or flows with free surface or flows with free surface or flows with free surface, different types. There are different types of flow. First definition is that uniform or non-uniform flow. I am clubbing these different types depending upon the same category, uniform and non-uniform flow. Now, uniform and non-uniform flow. Uniform flow is defined where the average velocity and depth of flow remains constant in the direction of flow. Now, that means if we write here, if you draw here, that means if the depth of flow H remains constant throughout. That means in this case, and obviously the average velocity will be constant. sorry, if the depth of flow remains constant in the direction of flow, average velocity also will be constant. This happens if the bed of the channel and the free surface runs parallel to each other, which gives a constant depth of flow in the direction of flow along with a constant average velocity of flow. This flow means uniform. Non-uniform flow is a flow where both depth of flow and accordingly the average velocity of flow varies in the direction of flow. Depending upon the degree of variation, this non-uniform flow is categorized in two types. One is gradually varied flow, where the variation in depth of flow and the average velocity of flow is gradual, not rapid or not very abrupt, and another is the rapidly varying flow. These are again the terminologies, rapidly varying flow, where the depth of flow or the average velocity of flow varies at any section very rapidly, so that is rapidly varying flow. So gradually varying flow is like that, the depth. This happens because of some control structure in a channel. For example, flow over a spillway in a dam. So what happens? The water level is like this H, it gradually varies like this because of this spillway. So here H and V average both vary, but vary gradually. So this is the depth, this is going to vary. So depth of the flow is varying, and accordingly the average velocity V average. So this is known as gradually, this is an example of gradually varied flow. Under some situations of flow with a free surface, we see that there is a variation. This is the channel, there is a variation from a lower depth of flow, okay, to a higher depth of flow, sudden variation. So the depth of flow varies very rapidly, so that the flow becomes, the flow velocity V average and the depth of flow H varies very rapidly. From a very lower depth of flow, it suddenly jumps to a very higher depth of flow, and V average also changes very rapidly. This situation is known as hydraulic jump, which we will discuss afterwards. Due to certain changes in the geometry of the channel, the hydraulic jump takes place. This happens when the flow changes from one kind to other kind. This flow is known as rapid flow in the upstream direction, that we will discuss afterwards, and the downstream flow is known as tranquil flow. That means in a transition from a rapid flow to tranquil flow, certain situations, certain kinds of flow which happens because of certain changes in the geometry of the channel, then the depth of flow and the average velocity varies very sharp or abruptly. So therefore, depending on that, so therefore this type of flow is known as rapidly varying flow. Both these flows are non-uniform flow. It's a gradually varied flow, the non-uniformity is gradual, and the rapidly varying flow at the non-uniformity is very rapid. Now the next demarcation is that steady and unsteady flow. Steady and unsteady flow. Steady and unsteady flow, we will not go for any further discussion. Already we have discussed that steady flow is a flow where all flow parameters are invariant with time. That means flow velocity or any hydrodynamic parameter, depth of flow or any parameter at any point is invariant with time. While when it varies with time, the flow is termed as unsteady flow. So variation of flow parameters with time at any point is termed as unsteady flow, and when it is invariant with time, this is steady flow. Another is the laminar flow and turbulent flow. So laminar and turbulent flow we will discuss afterwards. So beyond a certain Reynolds number for any kind of flow, flow changes from a laminar to turbulent flow. Turbulent flow is a flow situation where velocity varies random with time, and these random fluctuating velocities occur in three directions, which is the main characteristic feature of the turbulent flows, for which an extra momentum exchange in the fluid takes place and which increases the shear stress at the wall. So the flow changes from laminar to turbulent depending upon certain Reynolds number. So Reynolds number is the criteria for any flow. We will discuss it afterwards when we will talk about turbulent flow. Now Reynolds number is the criteria for the change of flow from laminar to turbulent in any class of flow. So therefore, this Reynolds number should be well defined for that class of flow. In case of a channel flow, Reynolds number is defined as the product of, we have come across this Reynolds number earlier in the principle of similarity and many other problems like problems in pipe flow, that rho into average velocity in the direction of the flow, rho v by mu, and this characteristic dimension is the hydraulic radius. So the definition of Reynolds number in general is the rho times some characteristic velocity times the characteristic geometrical dimension by the viscosity of the working fluid. So here the characteristic velocity is the average velocity in the direction of flow, and the characteristic geometrical dimension is the hydraulic radius. So by this way, if we define the Reynolds number, then the criteria for laminar flow, that when Reynolds number is less than 600, the flow in an open channel remains laminar. When the Reynolds number is greater than 600, the flow becomes turbulent, and all the characteristics for the turbulent flow is present, which we will now discuss. Which we will not discuss now, we will discuss in the context of turbulent flow. Now another differentiation is the tranquil and rapid flow. Now this difference is that the differentiation between tranquil and rapid flow is that under certain situation of flow, if you make an disturbance in the downstream, the disturbance can move to the upstream and can change the upstream condition, and the flow situation is changed. This is one situation of flow that takes, in one situation of flow, any disturbance in the upstream, in the downstream, if you create any disturbance in the downstream, that signal reaches the upstream and changes the condition there and changes the entire flow situation, flow condition. This type of flow is known as tranquil flow. And under certain situations of flow, any disturbance in the downstream doesn't reach to upstream condition. That signal doesn't reach to upstream, and the flow conditions at the upstreams are not altered. So depending upon this criteria, whether a disturbance at the downstream, disturbance created at the downstream reaches the upstream or not, the flow is divided into two categories. One is the tranquil flow, another is the rapid flow. The flow is tranquil flow when the disturbance created at the downstream reaches the upstream and changes the upstream condition. And rapid flow is a flow where the disturbance created at the downstream cannot reach the upstream and cannot change therefore the upstream condition. So this therefore, whether the flow will be tranquil or rapid, depending upon simple condition that the relative magnitude of the flow velocity and the velocity with which the disturbance created at the downstream moves towards the upstream. That means the velocity of propagation of the wave which is moving as a disturbance, as the signal of the disturbance in the upstream. And if the velocity of the flow is more than that velocity, so this signal will not reach. If the velocity of flow is less than the velocity of propagation of the disturbance wave, then the disturbance will reach the upstream. So therefore it depends upon the magnitude of the flow velocity and also the magnitude of the velocity of propagation of the wave that is generated due to the disturbance at the downstream. And this depends largely on the gravity, local gravity. So therefore local gravity and the flow velocity decides whether the flow will be tranquil or rapid. And this is characterized by a dimensionless term known as Froude number. As you have already seen earlier in the principle of similarity, Froude number is the ratio of the inertia force to the gravity force. Now if you write the Froude number, well, Froude number Fr, which is defined, earlier we defined as V square by G some characteristics length L. Here the Froude number for free surface flow is defined just the square root of this V by root over, this is the average, V average velocity by root over G into RH. RH is the hydraulic radius. So therefore, depending upon the value of this Froude number, we define whether the flow is tranquil and rapid. For tranquil flow, Froude number is less than 1. For rapid flow, Froude number is greater than 1. So tranquil flow Froude number is less than 1, and for rapid flow, this RH sometimes is substituted by the depth of the flow. That means Froude number is defined as V average by root over GH, simply the depth of the flow. So, tranquil flow, Fr less than 1, rapid flow, Fr Froude number greater than 1. So, we see the different types of flow, that uniform and non-uniform flow. Non-uniform flow are two types, gradually varied and rapidly varying flow, depending upon whether the variations of H, depth and average velocity is gradual or rapid. Then steady and unsteady flow, laminar and turbulent flow, tranquil and rapid flow. Now I come to a derivation for flow through a uniform flow, rather I must write uniform word, uniform flow through a straight channel, through a straight channel, uniform flow through a straight channel. Let us consider a straight channel like this, and let us consider a uniform flow, that means the free surface is parallel to the, this is the free surface, parallel to the bed of the channel, this is the bed of the channel, which makes with the horizontal, this is the horizontal line, an angle theta. That means an incline with horizontal, and this is the free surface, and the flow takes place in the uniform flow takes place. What is the expression for the flow velocity and the rate of discharge? To do that, we take a control volume, a simple control volume like this. Let the control volume like this, we take A, B, C, D. Now, what are the forces acting on the control volume? There is no force acting on the free surface of the control volume. On this surface of the control volume, adjacent to this bed, solid bed of the channel, the force acting is the shear force, tau. That is denoted by the shear stress into the area. That is the shear stress acting in opposite direction to the flow. At this surface, the pressure force is acting, at this surface, pressure forces. Now, in case of a flow in a channel, that means flow with a free surface, the pressure force over the area is the hydrostatic force. So, it is like this, the variation of the force is like this. As you know, the hydrostatic force is linear with the depth, so this is the hydrostatic force acting. Similarly, on this surface also, the similar way the hydrostatic force is acting. And there is no change in the static force. That means what I told you earlier also, at any height h from the bed, the static force at this point and static force at this point remains constant, because this is atmospheric pressure plus this height which is remaining constant. So therefore, in case of an uniform flow of this type, the pressure forces acting on this surface AB and CD balance each other. Now, since the force is steady, we can tell that if you consider a fluid element as a system, that is the net force acting on this fluid element is 0. Or from the momentum principle, we can see that if we define it with respect to a control volume, that is the net rate of momentum efflux from the control volume, because under steady state no momentum is being generated or is being accumulated in the control volume or is being depleted in the control volume. So the net rate of efflux of momentum in the control volume must equal to the net force acting on the control volume. And for a uniform flow, the net uniform flow or the steady flow, the net rate of efflux, steady uniform flow, this is also steady uniform flow, the net rate of efflux from the control volume is 0. So therefore, net rate of efflux, if you take control volume from the control volume is 0 for a steady uniform flow. Because for steady flow there is no rate of change of control volume within the flux, only the net of change of momentum within the control volume, and for uniform flow net rate of efflux from the efflux, net rate of efflux of momentum, x direction momentum, let we take this as x direction, from the control volume is 0 for uniform flow. From a system approach, we can tell that the rate of change of momentum of the system is 0, which ultimately gives the same thing, that net force acting, that is the net force acting on the control volume or the system, if you take a system approach, is 0. So what is the net force acting on the control volume? If we take the net force acting on the control volume, we will see that net force acting is the W, weight, and the shear stress, that the shear force at this plane. So if you make the force analysis in the direction of this, now if we make this, now we will see that this angle is 90 degree minus theta, because the angle with the horizontal is theta. So this is a parallel line to the bed in the direction of flow, with the vertical will be 90 degree minus theta. So simply we can write W sin theta is equal to the frictional force, that means tau W, into the area will be that if we denote this length of the control volume in the direction of flow as L, it will be P into L. Well, so now W is the mass times G, so we can write therefore tau W P into L is equal to W is the mass is density into A into L. A is the cross-sectional area of the flow. So A into L, this is the mass of the control volume, into G into sin theta. All right. Now we see that we now substitute this tau W in terms of a friction coefficient, We know that we define the friction coefficient in a flow, as we discussed in pipe flow problem, as the general definition tau W, the wall shear stress divided by the dynamic head. And in case of this flow, as similar to that of flow through a closed conduit or duct, the dynamic head is based on the average flow velocity. So therefore, with this definition of friction coefficient, I can replace tau W as F into half rho V average square. So tau W, if I write half rho F into V average square into P into L, here we can write rho A L G, and this sin theta is replaced by S, where S is known as the slope of the channel. S is sin theta, and for small angle it can be equated to tan theta also. Then what we see, rho cancels, L cancels. So simply we can write V average, the flow velocity, is root over 2G by F into, now A by P is RH, that is the hydraulic radius, we have already defined, RH into S, root over RH into S, or simply we can write in a different fashion 2G by F whole to the power half into RHS whole to the power half. Now usually all flows through the channel is turbulent flow, that means Reynolds number is greater than 600. And in turbulent flow, the friction factor, as we have discussed earlier, is usually independent of Reynolds number or the flow velocity. So therefore friction factor works as a constant parameter, G is constant, so that this is RHS whole to the power half. So this equation gives, is well known, this is a very popular equation, that average velocity of flow through the channel, that means this average velocity of flow through this channel is given by a constant times RH, the hydraulic radius of the channel, into the slope of the channel to the power half. This is known as well known Chezy equation, depend on the after the name of the person who first derived this, Chezy equation. And the C is known as Chezy's coefficient. This C is known as Chezy's coefficient. Okay, C is known as, this constant C is known as Chezy's coefficient. Now therefore we see the Chezy's coefficient depends upon the friction factor. So we will discuss the Chezy's coefficient in the next class. Okay, thank you.